Here are solutions to homework set number 10 for ECE 376. Now in this homework set, we're looking at Time1 Capture, Time1 Compare on a PIC 18F4620 microprocessor. Starting out, the first problem is I want to measure your reflex time. So here's kind of the idea. What I want to do is press the button, RB0. When I press it, between 3 and 7 seconds later, the lights turn on port A. When they turn on, I hit the button again and record the time difference. And this is in milliseconds. So I'm going to press the button. 3 to 7 seconds later, the lights on port A turn on. There, they just turned on. I hit the button, and I hit the button 2479.6017 milliseconds later. So let's try that again. Hit the button, wait for the lights to turn on. There, 188.4994 milliseconds. Okay, how do we do that? Well, I'm actually going to use 3 interrupts plus the main routine. What that means is you actually have 4 flowcharts running. On reset, the main routine sets up the interrupts, waits for a button, like here. I hit the button. I then wait 3 to 7 seconds. The lights on port A turn on, like right now. I wait for the button to be pushed. When I push it, display the time difference, repeat. Timer 1 interrupt interrupts every 65,000 clocks, 6.5 milliseconds. It doesn't really do anything except keep track of time. Capture 1 measures the rising edge on port A pin 2. So right here, the orange wire is capture 1, the lights. When the lights turn on, the time of the edge is captured on capture 1 interrupt. So there, just capture the time. When I hit the button, RB0 is connected to RC1. Hit the button, that records the time that I hit the button. The time difference was 7.934 seconds. Not a very good one. Okay, so that's the flowcharts. Kind of note, when you have interrupts, the only way I figured out how to do interrupts in a flowchart is you need separate flowcharts for each interrupt. The main routine keeps on looping. It's running over and over again, kind of like you see. The interrupts do not loop. You get in, get out quickly. If you see looping inside an interrupt, you got a problem. The corresponding C code. I'm only going to look at part of it. Here's the interrupt service routine. Every 6.5 milliseconds, I increment time. Doesn't really do anything, just time. Timer 1 keeps track of time. On the rising edge, this is when the lights turn on. Record the time of the lights. When you hit the button, that's capture 2. Record the time of the button and the time difference. Record that. Main routine sets up everyone. Well, here's the main loop. Wait for the button to be pushed. Calculate a random number between 4 and 7 seconds. Wait that long. Turn on the lights on port E, on port A. Wait for the button to be pushed. Then display the time difference. This line right here, that's actually just so I can tell something's happening. Let's try this again. So port E, over here on the left, turns off. As soon as the lights, when I start, there. This is the 3 to 7 counter. Second counter is turned on. That just lets me know something is happening. Then the lights turn on. It's always nice to have a little bit of feedback so you know if the code is dead or is actually doing something. All right, once you get your code working, you can do something with it. First part is to validate your code. If I modify the code so I display the time delay, I display that right at a little short snippet routine. And the time delays were 6.4, 5.9. Time delays between 4 and 7 seconds. That looks good. I can check the interrupts. Let's do that again. Let's make it a 5-second delay. There we go. E's turned on, so it is counting. When the lights turn on, 1, 2, 3, 4, 5. That should be 5 seconds. It was actually 4.817 seconds. Okay, it looks like the interrupts are working correctly. Once you've validated your code works, I can now start collecting data. So for collecting data, it was letter rip As soon as the lights turn on, hit the button. 179.1023 milliseconds. Insane number of decimal places, but they're all meaningful. Pick and do that. A single data point tells you nothing. You need to take a couple data points. So here I took 5 measurements. With 5 measurements, I've got a mean, standard deviation. So what that tells me is my reaction time should look like this, bell-shaped curve. The mean is 192 milliseconds. Standard deviation is 7. From that, I can tell you the 90% confidence interval. Doing a t-test with 5% tails, sample size of 5, meaning 4 degrees of freedom. I need to go left and right. 2.12 standard deviations from the mean. Gives me the 90% confidence interval of 177 to 208. So 90% of the time, that should be my reaction time. Okay, so that was the first one. Just kind of having fun with Time1 Capture. With Time1 Capture, you can measure time insanely accurately. Next problem. This is a different one. So for this problem, what we're going to wind up eventually is a little game. What I want to do is determine whether I can tell the difference between 2 notes. So initially I'm going to have 2 notes, E4 and F4. When I hit the button, it's going to play the first note E4, then F4. If they're the same, I hit the top button, RB1. If they're different, hit RB1. The same, I hit RB0. So say I think they were the same. Nope, they're not. That was wrong. Wrong again. Correct. Okay, so that's the idea. I'm going to do that with 2 notes. I can clearly tell the difference, E4 and F4. And then I'm going to do E4 followed by E4 plus 0.1%. So starting out, I want to come up with a program that plays 2 notes. And do that using Time1 Compare. So the first part is do the calculations. How many clocks between interrupts at E4 and F4? So here's 15,000, 14,000. With the interrupts, I can have Time1 Capture 2. Play that on port C pin 1. I'll toggle the note every time, set up the next interrupt, and end 2 clocks. Then in the main routine, I'll make N2 15196, that's the note E4. Play it for 500 milliseconds, go quiet for 200 milliseconds. That's what play does, turns the note on and off. Then I'll switch over to F4. Play that for 500 milliseconds, then wait a second. So if I try that, here's what's going on. When E4, F4. Okay, so far so good. Once you get that to work, rather than having it play the 2 notes always different, do a coin toss. One way to do a coin toss is use timer 1. So every time I run it, I'll look at the time that I hit the button, mod 1, or and 1, mod 2. This is either going to be true or false. If it's true, I'll play the same note twice. If it's true, I'll play different notes. False, I'll do the same note twice. So modify the code, compile it, download the code, here I hit reset, get my welcome message, download the code, time passes. So here's the code downloading. It's now running, so I'll start the program. Those 2 notes were the same, I'll hit the bottom button. And I was right. Same note again. Same note again. Different. Same. Same. Different. So here you can clearly tell the difference. That shows up on a chi-squared test. I was right 10 times, wrong 0 times. I can check to see if I'm guessing. If I'm guessing, I should be right half the time. I was actually right 10 out of 0. To calculate the chi-squared score, take the difference squared divided by expected value, difference squared divided by expected value. Add them all up, I get a chi-squared value of 10. From StatTrak, 1 degree freedom, chi-squared square of 10, means I'm 99.8% certain I'm not just guessing. Could be chance, but it's kind of hard to go 10 and 0 if you're just guessing. So everything looks good. I can clearly tell the difference between notes E4 and F4. Let's try E4 and E4 plus 1%. So in the code, I'm looking for the number 15184. Change this to 15184. That's plus 1%, so these two notes are different. Part of the reason we're doing all this is you're trying to convince yourself, does the code work? I'm fairly convinced right now that the code is flipping a coin. It is playing the first note always, the second note 50-50, whether it's the same note or different note. I could tell with E4 and F4. Now let's try E4 and E4 plus 0.1%. So give me it a try. Here's the two notes. Same or different? I think they were different. Hey, I was right. Different. Same. I can't really tell. Different. Oh. Okay. So I really can't tell the difference. But I can tell when I do a chi-squared test. Am I really guessing, or is it just, or can I really tell? Well, when I tried it, I was right 8 times, wrong 8 times. This last one I was 4 and 2. Keep going for a while. I can check, well, this is going to tell me that I'm just guessing. Half and half. Just for fun, this was not part of the homework set. Let's try some differences. Suppose the difference is 100 clocks, 0.65% change. When I did that, I was right 12 times, wrong 0, saying I can definitely tell the difference of 100 clocks, 0.6%. Can I tell the difference of 50 clocks? Yeah, I could actually tell pretty well. Can I tell the difference of 25 clocks? Now it's getting kind of iffy. Okay, so let's have some fun now. Can I tell the difference of 100 clocks? So here's the difference of 100 clocks. Same. Same. That's 100 clocks. I'm having a hard time telling the difference. Okay, try that again. Recompiled the code, downloaded it. Same. Same. There's a slight difference there. Hear that difference? Okay, so that was 100 clocks. I could try that again with 50 clocks. So to do that with 50 clocks, bring that down. I'm going to go from 15,191 to 15,141. Difference of 50 clocks. Compile. Download. Can it tell the difference of 50 clocks? Wait for it to finish downloading. Okay, now it's ready. I think that was different. Same. Different. Different. Same. Same. Different. And so on. So you can do kind of experiments. When I tried that, difference of 25 clocks, I was kind of guessing. 15 clocks, totally guessing. At 50 clocks, I could tell the difference. At 100 clocks, definitely tell the difference. So based upon this, I conclude that I can tell the difference of 0.3% or 50 clocks. Pretty certain, 99% certain. Below that, I'm pretty much just guessing. That's some of the power of a chi-square test and a PIC processor. I can ask a question, set up a double-blind experiment, and answer that question. So that's homework set number 10 for 376.